Hey guys, this is the third video on conditional probability. This one will focus on finding conditional probability with frequency tables, which we've already dealt with, and also talk about the test for independence. So if you look at the slide to your left on the screen, it's a frequency table, which shows, as we're assuming here, preference of chocolate or vanilla with the gender of female and male. So given these values, we should always make sure, of course, that we put in our totals. So got a 2x2 box here. The first thing we want to do is find all of our totals. So the total for chocolate is 59, for vanilla 30, for male 45, and for female 44. So our total is 89. The first question we are asked, and I'll go ahead and number it, number 1, is to find the probability of male and vanilla. So remember that unless it's otherwise specified, your denominator will always be the total. If we look at our table when we're looking at finding the probability of M and V for vanilla, then we want to find the intersection of male and vanilla. And on our frequency table, that value is 13. So the probability of male and vanilla is 13 out of 89. Next, we are asked to find the probability of male given vanilla. What's different this time is similar to in video 2 where I talked about the given always being your denominator. We need to make sure that on the frequency table we are looking at the total for vanilla. So what this is saying is ignoring chocolate, given that we know that they like vanilla, and there are 30 of those. How many of these 30 are male? How many of the 30 that like vanilla are male? And that is 13. So I'll actually write that out there and how you would interpret it. How many of those that like vanilla are male? How many of those that like vanilla are male? And that's 13 out of the 30. And last, you are asked the probability that someone likes chocolate given that they are female. Probability that someone likes chocolate given that they are female. Well, if that's the case, we want to concentrate on only the females. Again, the given part, just like up here, vanilla total was 30. We're going to use our female total. And our female total is 44. What it's asking is how many of those 44 like chocolate. So again, if we look back at our frequency table, of the 44, there are 27 females that like chocolate. So our probability is 27 out of 44. So remember, what's different is the given, the denominator changes. Your sample space changes to whatever the given is. Next, going our way. Here we go. Next, we want to look at the conditional probability formula. So if you look at the slide on the left, it says, to make things easier, there is a formula to find conditional probability. So I can tell you that in general, we can use the and value as our numerator and the given value as our denominator, but we do have a formula here. And this is what you're going to want to use when you have word problems that do not refer to a tree diagram, frequency table, or Venn diagram, frequency table, or tree diagram. So it says the probability of A given B is the probability of A and B divided by the probability of B. If you look at this, that's actually what we did right here for this example. Let me move this thing out here. So we said that the probability of A and B is the intersection. So similar for number 3, where it said chocolate, given that they're female, we found the intersection of chocolate and female, and that was 27. That's our and value. So that one is what goes up top. On the bottom is always going to be the probability of your given. So notice, just like I did up here with vanilla, that was the vanilla total, female total, we would put the B total here, or the probability of event B. Okay? So this formula is what we're going to use on the next slide. So what I want you to remember is to use your and on top and your given on the bottom. And on top and given on the bottom. Example 7, if we refer back to the PowerPoint slide, it says Aaron and Tyreek are study buddies. The probability that Aaron aces the test is 70%. The probability that Tyreek aces the test is 73%. And the probability that both ace the test is 60%. So first, let's kind of digest the information given here. What we know is that the probability that Aaron aces his test is 70% or 0.7. The probability that Tyreek aces his test is 73% or 0.73. The probability of Aaron and Tyreek both acing their test is 60% or 0.6. That's what I would do first when looking at a word problem. That way you have all the values you need to answer your question. So I'm going to look at the problem below the question below the problem saying find the probability of Aaron given Tyreek. So this is what this is asking is, what's the probability that Aaron will ace his test given that Tyreek aced his test? Well, think about this formula up here. Really, all we want to do is let Aaron, A equal Aaron and our B represent Tyreek. So if we basically use this formula, but in place of A and B, put A and T, it would look like this. The probability of Aaron and Tyreek divided by the probability of the given, which is Tyreek. Well, luckily, we already know these values. Look here. We have here the probability of Aaron and Tyreek. We also know the probability of Tyreek. So really, all we're going to do is plug in our values and simplify. The probability of Aaron and Tyreek is 0.6. The probability of Tyreek is 0.73. We divide those by typing it into our calculator, 0.6 divided by 0.73, and we will get 0.82. And that would be our answer. Okay? Next, it asks us to find the probability of Tyreek given Aaron. Similar to our what we just did with our conditional probability formula, is and over given. Only this time, it's the probability of Aaron on the bottom. So similar to what we did before, the probability of Aaron and Tyreek, this number is going to go here, and the probability of Aaron will go here. So the probability of Aaron and Tyreek was 0.6. The probability of Aaron is 0.7. We simply type that in our calculator and get 0.86. Note that I am converting this, or I know if I need to round that I would round to 2 decimal places because of the significant digits, meaning in my probabilities I had 2 values, 0.73. And of course this was 70% and 60%. Okay. So, of course, because our answers, we have answers right here as decimals, we want to think back to our problem. So if it's asking us probability, yet the probability in the word problem was as a percent, we should convert this now to a percent by moving our decimal twice or multiplying by 100%. And, of course, that would give us 82%. And for Tyreek given Aaron, 86%. And that concludes that problem. We're next going to finish up with the test for independence. The test for independence is basically a method for determining whether 2 events are independent. We've already talked about independent events, meaning that if we have two events where the outcome of the second event is not affected by the outcome of the first event, that they would be independent. So for independent events, basically, if we look at the probability of A times the probability of B given A, it's really just the same thing as the probability of A times B if they're independent. Remember when we talked about multiplying independent events, all we had to do was to find the probability of A and B was to multiply the probability of A times the probability of B. Well, all we're going to do now is test if they're independent to see if the probability of A times B is equal to the probability of A and B. That's really all we're going to do. So even though it has more complicated language here, what I really want you to understand is just like in the slide, it says the probability of the individual event times the probability of the individual event. If it is equal to the probability of both, then they are independent events. Independent events. So we're going to try this next. Example 8 says to determine whether these two events are independent or dependent. It says Pablo and Eric are shooting hoops. The probability that Pablo makes a free throw is 0.45. The probability that Eric makes a free throw is 0.67. And the probability that they both make it is 0.3015. So exactly what we do with this test for independence, even though the language looked maybe a little confusing, don't let it confuse you. Just understand that this is basically what the rule says. We want to take the individual probabilities, which means we would do the probability of Eric times the probability of Pablo, and check to see if it is equal to the probability of Eric and Pablo. And if it is, then it's independent. So from the paragraph, it says probability that Pablo makes it is 0.45. So I'll just do it this way. And then the probability that Eric makes it is 0.67. And we want to test and see if it's equal to the probability of 0.3015. So all we need to do is pick up our calculator and multiply these two together. Type it right in your calculator. 0.67 times 0.45. And in fact, it does equal 0.3015. So this is exactly the work I would want to see when you do this problem. Show that they either are or are not equal, and put a check and write independent. They are independent because the product of the individual probabilities is equal to the product or the probability of both. So let's say that after doing a problem, you end up getting like 0.3015, and you were trying to test it, it came out to equal 0.4716. Of course, they would not be equal, so of course I'd want you to show what you're multiplying, but because they're not equal, simply put a slash through the equal sign, and that slash means not equal to, making the events dependent. Okay? So simply take your given probabilities for each, see if the product is equal to the probability of both. And that concludes our lesson on conditional probability.